Welcome to Working with Big Data in SAS. My name is Mark Jordan, and I'll be your tour guide through the next few minutes as we discuss working with data and the impact of data size on program performance. In order to better understand how this works, we need to understand how the data flows through SAS in both the traditional SAS 9.4 architecture and in the new SAS VIA architecture. We'll also look at identifying bottlenecks in the processing, and we'll identify some thumb rules in order to mitigate those bottlenecks. So the simplest form, we have SAS installed on a computer. SAS requests a file from the operating system. The operating system moves that file into memory by blocks, and then SAS processes that data one row at a time in its own memory space. In this default mode, all rows and all variables are read in, and when we're done processing, all rows and all variables are written out. Now, disks are electromechanical beasts, and getting data from a disk is about 1,000 times slower than moving data around in memory. So if we could somehow minimize the amount of physical data stored on the disk, we could possibly improve throughput of our process. Compressing data is possible in SAS, but you have to remember that nothing is for free. So when you compress the data, it does reduce the size on the disk. That may improve the I/O speed, but the data then has to be decompressed using CPU prior to further processing. The areas of usual concern for us are that all the data rows from the original data set are not required for our processing generally. Now, there's two ways of controlling what data gets output in SAS. One is to suppress the outputting of data with a subsetting if statement, for example. But there's another way, is using a where statement to subset the amount of data that is ingested by the process. And if we can reduce the amount of data we're taking in, as well as the data being written out, because if we don't take it in, it can't get written out, then we should speed up the process. So a good rule of thumb, number one, is if using a where and a subsetting if statement would produce the same results, use the where. Not always just about rows, but it's also about columns. Some data sets are extremely wide, and we only need a few of the variables in that data set for our process. Now, again, there's two ways of approaching this problem. We can use keep or drop statements in the SAS code, and this suppresses variable output. But if you don't need that data at all for any of your processing, you can reduce the size of the data ingested by using a keep equal or drop equal data set option on the set statement. This can reduce data movement again, both in and out, and can save considerable compute resources. So thumb rule number two, if a keep equal and drop equal data set option on the set statement will produce the same result as a keep and drop statement in the code itself, then use the data set option. One of the things I don't understand is this underutilization of the SPDE engine in base SAS. The Scalable Performance Data Engine in SAS ships with base SAS. And if you have multiple disks available, now this is not a thing to be tried on a single spindle. If you split this up on a single disk drive, it's not going to help. But if you have multiple disks on your system, then you can spread your data up physically across those disks, and when you call for the data set to be read in, it can be read in parallel, resulting in a significantly reduced time to move the data physically to and from the disk. Only base SAS is required, and it's really not that difficult to set this thing up and use it. Here is a typical live name statement using SPDE. In the data path, we show the folders on two different drives that are holding the pieces of the data. This was actually done on my laptop using an SD card as the second disk. And then when I read in this humongous data set, right, reading it from a traditional SAS data set stored on the hard drive took almost a minute. Reading it, same data set, through SPDE reduced the time by a full order of magnitude. So another way of speeding up your data. In today's world, though, the data size is important, but we do complicated things to our data, and it's not unusual to have a process that is not I/O bound, but is CPU bound instead. You can tell this by looking at your SAS log and see if the elapsed time in the log is very, very close to the CPU time. And if it is, it's very likely your process is CPU bound. In most modern systems, we have many CPUs available, but the SAS data step runs single-threaded. This can be a little frustrating. And we have long yearned for an easy and safe way to parallel process data in SAS. Well, rejoice. With the release of the SAS 9.4 version came a new language called DS2. DS2 is kind of like a melding of your traditional data step language with a little bit of SQL. DS2 was designed from the ground up to parallel process, and it can parallel process right on your SAS platform and use all of those extra lovely CPUs. An I/O bound process usually won't benefit from DS2 because we have a single read thread, as you can see. But if you have a truly CPU bound process, this can dramatically speed up your processing. So if your data step process is CPU bound, you should consider rewriting that in DS2 to take advantage of threaded processing. And this can be done with nothing more than base SAS. In today's world, though, frequently our data doesn't live on the same machine where our SAS process lives. We frequently use data stored in database systems. We get transparent access to that via the SAS Access LibName engine, which makes connections to the database and retrieves data for us to process. So here you can see that when we request data from the database, the Access engine turns that into SQL code, which then retrieves the data or a subset of the data from the database and sends the data back over the network to the SAS platform for computing. If you are using this type of setup, there are many opportunities to improve the process. Number one, most database systems are fairly well provisioned. They have many CPUs, many disks, and so you're getting fully distributed I/O as well as application processing. So they're very, very fast at subsetting, aggregation, sorting, those types of things. The result set has to be passed back through the network, and so if we can reduce the amount of data movement, we can definitely make this thing go faster. So first off, if you use those keep, equal, drop, equal data set options on your data set in the set statement, this will surface on the database side as a select list, reducing the number of columns that are returned to SAS. In addition, if you have a where statement in your SAS code, this will definitely surface in the SQL on the database side, reducing the number of rows ingested. These two techniques can dramatically reduce the amount of data movement over the network. So remember, thumb rule number 2 was if you could use a keep equal, drop equal, do it instead of a keep or drop. And thumb rule 1 was if your where and if would produce the same result, use where. These rules are even more important when you're accessing data in a database. All right, so working with database data, we really want to maximize the amount of processing that happens over on the database platform. Why? Because it has all that lovely parallel processing hardware, right? We can improve the process we talked about before by being very careful to keep our where expressions as ANSI as possible, using things like instead of maybe SAS constructs like contains, can be easily translated into code that will run on the database. Whatever you use in your workflows that cannot be translated, SAS will do its best to do as much subsetting as possible on the database, but then it will have to bring back a larger subset in order to finish that process in SAS. For example, here's a where statement that gets all of the rows of data that begin, where the customer name begins with Silvestro. And when we executed this where statement on the SAS platform, it took 6.5 seconds to return the answer, right? Rewriting that with a ANSI expression, the like operator, we can say like Silvestro, so it begins with Silvestro, but it can have as much information following as we like. That converts straight into SQL, and you can see that the real time, again, reduced by an entire order of magnitude, as that was all handled in parallel on the database hardware. So this brings up another rule. If you write your process in SAS in SQL or the new FedSQL language, most of that code can process entirely in the database. So a good rule of thumb is, if it's possible, write the process in SQL. In other words, if you could do the same thing in dataset or SQL, the results are going to be the same, and you're dealing with database data, write that process in SQL. If that doesn't work, consider using one of these base SAS procedures that are capable of generating some very sophisticated SQL for processing in a database. Proc_freq, proc_means, proc_summary, tabulate, report. They can all do ordering of your data, pre-summarization of your data, so that much smaller data set subsets come across the wire, and this can dramatically improve the speed of your process. So if you can't do it in SQL, consider using one of these enhanced base SAS procedures that can generate sophisticated SQL on your behalf. And of course, if that doesn't work, then go ahead, use your data step. Keep everything as ANSI as possible. Use our thumb rules with set, keep equal, drop equal, and where statements, right? But just be aware that whatever couldn't be done on the database platform will then have to happen on SAS, so it may take just a little bit longer. But you may be able to do much more complicated things. Say, but I don't want to just execute the SQL in database. I want the whole data step to run in parallel in the database. Well, if we could just take our code to where the data lived instead of having to bring the data out to where the code lives, we could really improve the throughput of this process. And that is the basic idea behind the SAS in-database code accelerator. This gives us the ability to execute native SAS code on massively parallel databases, and basically negates the need to move the data at all. So the SAS in-database code accelerator is currently available for Teradata, Hadoop, and Pivotal Greenplum. You need both the SAS Access Interface licensed and the in-database code accelerator licensed and configured. But this enables some traditional data step and almost all DS2 data and thread programs to execute directly in the database. So when we have the in-database code accelerator installed, you can see that there's extra software on the database platform. In this case, we pass the code straight in as DS2 code. That executes completely in parallel on the database platform. Nothing comes, if you're reading and writing from a database table, nothing comes back to SAS but the log, which is outstanding. So thumb rule number 6 is, if your data source is on a supported platform and you have access to this code accelerator, do not hesitate to use DS2, because it is likely to make amazing improvements in efficiency and throughput of your code. Say, but my data comes from multiple sources. It doesn't just live in Teradata. It doesn't just live in Hadoop. So the in-database code accelerator is cool, but Well, let's introduce you to SAS Viya. SAS Viya is our latest iteration of the SAS architecture. It's specifically built to live in a massively parallel processing environment. The core of this whole thing is the Cloud Analytics Server, or Cloud Analytics Services, as it's called. And SAS is specifically designed to do machine learning and to manipulate big data. And hey, that's what we're all about. So what does it look like? SAS uses a shared memory model across a whole mess of computer nodes, which basically makes, if you have 10 computers with 100 gigs of RAM, then you have 1,000 gigs of RAM contiguous, is what it appears to be in SAS. You can load some pretty stinking big data into memory, and you can load more than one data set at once and persist it there. In MPP mode, SAS frequently delivers speeds 100 times faster than any other process that you can come up with. The cool thing about SAS is it can access data from a wide variety of sources with specially designed parallel load facilities that make it very, very fast to load data into SAS from different places. Once the data is loaded into memory, it persists there. It doesn't have to be loaded to and from disk for you to keep working with that data, which means that once it's loaded, all of the subsequent manipulation and work and analysis you do with that data no longer incurs that disk I/O overhead, which makes it lightning fast. The beauty of this is that with SAS as our back end, so to speak, right, we can get at this via an API and microservices from a variety of different front ends. So for instance, if you're a Python programmer, you can use Python to manipulate data up on SAS. But we're talking about SAS here, and of course SAS 9.4 M5 allows you to run data step code, DS2, many procs, that type of stuff right up there on the SAS server, fully distributed. It's really simple to do. You set up a little option to let SAS know how to find the SAS server. This is in SAS 9.4 M5. Use a SAS statement to create a named SAS session, so to speak. If the data you want isn't already in SAS, you can load your data up to SAS pretty easy with a thing called proc SAS util. Here I'm loading my big order fact table up into the SAS session. And if you use this promote statement, you don't need to, but if you do, that makes that data available and visible to other users on that same server. Once you're connected to SAS, I basically just run my SAS code. Here I'm reading from a SAS dataset, writing the results to SAS, and bam, that runs distributed on the SAS platform. Okay, so a quick review. Thumb rules for efficient SAS programming, right? When where and if statements produce the same result, use where. If keep and drop statements and keep equal and drop statements, or dataset options rather, will produce the same result, then use the keep equal or drop equal data statement to reduce the data ingested on the set statement. When you're writing your where criteria, keep your expressions as ANSI standard as possible so that the maximum processing can happen on the database. When you're reading from database data, write the process in SQL if you can. And if you can't, try using one of those in-database capable procedures like proc means, proc freq, proc summary. Right? And if that doesn't work, don't be afraid to use a data step, but it just might take a little extra time to execute. Look at your log. If your data step is CPU bound, you should consider rewriting that in DS2 to take advantage of threaded processing right there on the base SAS platform. Nothing but base SAS required. And if your data sources are on one of the supported data sets and you have the code accelerator, you should definitely write in DS2. And finally, if you have SAS 9.4 M5 and SAS Viya available, you should consider running just about everything up there because it is blazing fast. And now, any questions?